In this video, I want to prove a theorem that is due to essentially math overflow flow. So I'm going to put the link in an annotation. So maybe I'll put it like here. Okay, and so it's kind of a group thing. And it says the following. It says essentially that infinite products don't exist. So infinite products don't exist in the category of schemes. In the category of schemes over a field K. What I mean by this is the following. So we'll take a collection of schemes here over a field K that are quasi-compact. Okay, and if we suppose if we suppose the following, that this product it exists and it's a scheme, so it's represented by a scheme, and that there exists a closed point. So this is my notation for the closed points. If this exists, then for all but finitely many xi are affine. Okay, so this is the theorem that I want to prove. The proof uses a couple lemmas, but the most important thing is this thing called FPQC descent. We've talked about descent on the channel here, and I kind of want to remind you about descent and what I mean by this. So, so descent, a review real quick. And I kind of want to say like what I'm going to be using about this. So recall that okay. So let me say the output of the. Let me just, before we get into anything, let me just say the output of the theory. And this is what we'll be using. So it says that. So what we'll be doing is we'll be looking at like a morphism here of schemes, and we can base change this whole. So this is a morphism of S schemes. We can base change F by an FPQC covering as an so-called FP. So this is going to be a site, and this is a covering in the site here. So this is a base change by this, and then so what will end up happening is that this will induce say we'll get a new map, say from y prime, let's say y of s prime to x of s prime, and we can call this f of s prime. And then the idea will be that the main results of this series say that that if f of s prime is blah, so this is like an affine map or a closed immersion, then this will imply that f is blah. Okay, so this is the basic idea of what we're going to be using. So and let me say the important subexample of this particular example of the application of the theory is when S is spec K, S prime is spec K prime, and so that K over K prime is finite. So we'll be base changing by kind of a finite extension, and then concluding closedness or affineness of a map by the property over K. Okay, so let's go back to the descent review. Recall. So let's recall descent. So I kind of jumped the gun, but I'm going to write it again. So what we have is we'll take X the scheme, and then we have this associated site tau of x. And so tau could be like the FPQC type. So tau could be the FPQC site. So this is a site, and so maybe it's like a coverings. Okay, so this is a collection of coverings, and we're going to be looking at certain fibered functors. So we have these fibered categories. Fibered categories. F from the site of x to the category of categories. And so this is like remember, this is like a sheaf of categories. And we recall that what we're going to do is there's going to be a functor from so for each element of here, for each covering in here, for each element of a covering, we can associate a certain category. So like to open sets, we can associate the category of quasi-coherent sheaves over that open set. And to the global category, there's this descent data functor, where when we fix an open set, we can take descent here. And when this is equivalence of categories, we say that it is effective descent. So let's see. So effective descent means DD is an equivalence. Okay, that's what we have, and then there's some videos on this on the channel already. Okay, so let me give the example that's going to be important for us. When X is a scheme, we'll be looking at this particular fibered functor, QC, from the FPQC of X to so these covering to the category of categories here. And what it does is so f of, when we take a thing, u, so we'll say that we have u to x. So I'm going to write this as just u. This is going to be equal to the quasi-coherent sheaves on x base changed with u. So these are the quasi-coherent sheaves, and morphisms of quasi-coherent sheaves are the usual things. So morphisms as usual. Okay, so let me give another example. There's going to kind of be a sub-example here. So we're going to do, so X is going to be a scheme again. And I'm going to define FF from the FPQC. It's going to be a fibered functor on the FPQC topology. And what we're going to do is FF of U will be the set of, well, it's going to be this category where the objects are affine maps over X of U. Okay, and then morphisms are the usual thing. So y1 to y2 xu is like so. So these are the morphisms. Okay, so if we have one of these affine maps over xu, so given this thing, we can associate this sheaf. Notice that so we have this sheaf here, and actually knowing this, getting this is enough to get the affine map. The affine map. And again, affine maps are just maps where the inverse image of an affine set is affine, an affine open. So this is kind of an important example here. Let me give another example. Another fibered category. So I'm going to define, so X is going to be a scheme again. And I'm going to define F closed from the FPQC. It's going to be this fibered category on the FPQC site. And what it's going to do is it's going to take covers, elements of covers, and it's going to, closed. And it's going to take so it's going to take closed immersions. So notice that closed immersions are affine. So we really and then affine immersions are determined by the structure sheaf. So we really have kind of three inclusions. We have this FQC. This contains the affine things, and then this contains the closed things. And it'll turn out that there's a kind of a theorem. So the descent functors for F closed, FF, and FQC are effective. So we have this equivalence of categories. And this in particular will mean that we'll be able to test affineness or glue together quasi-coherent sheaves or quasi-coherence or closedness from descent data on the covers. So this is, I think, due to this theorem is due to Sayre and Grothendieck. And the main tool here is this kind of there's kind of this FPPF topology, and this faithfully flat descent and these type of things. So this FPQC magic, and there's a good chance that I'll do a video on this because I want to talk about these things in maybe a differential setting. This is one of the things that I want to talk about. That's unrelated to what I'm going towards now. Although I'm going to use this for some differential algebra stuff, this whole theorem. Anyway, let me just talk about how to apply this. Let me say again how we're going to apply this. Let me go to a new page. How to apply. Descent. So the idea will be, so how will we cook up maps? So sometimes we'll have a map here. We'll just have a scheme, and we'll have some FPQC thing. And so there's kind of a fact or theorem that we can base change FPQC maps to get FPQC maps. So in particular, this map, this is also going to be FPQC. And the way we should think of it is maybe sometimes I like to draw the base change the other way. So like you'd write S prime here, and then X is base changing, and then this would be the base change version of the map here. So we'd have the other way. So yeah. So sometimes we write this as X of S prime, but this is also equal to maybe S prime of X. Okay, so they're the same, and you can use this kind of to your advantage. And the important subexample again is when S is spec K, and then S prime is spec K prime, and K prime over K is some like finite algebraic extension. Okay, and so so when we base change, so the idea will be base changing some X over let's say spec K will give some XK prime to X, which is FPQC, and then the properties here will tell us about the properties of X that we're interested in. Okay, so to move forward now, we're going to start with the first lemma, lemma 1. The first lemma says it's about the shape of opens in products, and it says the following. it says for all u inside this big product, open, there exists a u prime and some I prime, where such that u is equal to u prime with this product, where we take over here something like this, and where the following is true, that u prime is this product of these guys. Sorry, u prime is in these guys I prime. These are this is open. So now this is a finite, and I prime here is a finite set, subset of I. Okay, so we want to prove something about this. I'm going to give you kind of a sketch of a proof of this. So the proof sketch. Well, okay, so so another thing in this theorem is that these xi's are quasi-compact. Okay, so the quasi-compact means it has the Heim-Borel property. Because it has the Heim-Borel property, what we can do is well, okay. So for quasi-compact things, maybe I'll leave something in the annotations if this is unclear. But so since xi is quasi-compact, then there exists some yi. This is for all I. This implies that there exists a yi that covers xi, where so this is a cover with that's affine. And so the basic idea behind this, let me just say what to do. You can cover this by affine opens. Any scheme can. And so what you can do is there's a finite cover of this. And so what you can do is you can take a disjoint union of the finite cover. And that's what we're going to do. We're going to take the disjoint union. All right. And so now what can we do? Well, now that we have these yi's covering, what we can do is we can take the product of the yi's and we can cover it. So we can take f, and this is going to be the product, if we call this map fi, the product of the fi's over I, and into the product of the xi's, and this is for I and I. And now what I'm going to do is I'm going to kind of prove something about the open sets here. So we're going to take an open here, and this is this map F, and what I can do is I can look at the inverse image over here. This thing's affine. This guy over here is affine. It's actually equal to, well, the product of these yi's for I and I. This is going to be, well, we knew this thing about tensor products. It's this big tensor product for I and I of these AI's. Okay, and I want to prove something. So this is an open here, and this is an open here. So the inverse image of an open is an open. And it turns out that we'll take this guy, and so F inverse of U is going to be contained in V, which is a principal open subset. So this is an open subset given by localization of a single thing. So if A is equal to, so let's just let me say this. So if A is equal to these products of these tensor products of these AI's, then this V looks like a spec of AG for G an element of A. Okay, so this is a principal open subset. Okay, so that's what a principal open means, and it turns out that G, well, it's going to be a sum of these tensor products, but will only involve let's say things from finitely many i's. So there exists some I. So in particular, so the V, well, this is going to be spec of AG, And it's actually going to look like spec of, well, the tensor product. And now here's where the finitely many comes in, of I, and then this thing here, G, crossed with spec. And now the tensor product is going to go over I not away from I prime. And the G is not going to touch this part. Okay, so we have this. Okay, so this is how this is going to look here, and these are finitely many, finite tensor product. So there's only finitely many appearing in the sum there. Okay, so so this means that U is going to be contained in f of v, and we can notice that pi, when we project away from U, this will imply that this looks like this whole thing here. And so this is the sketchy part. So I'm going to say that U is going to be pi inverse I prime pi I prime of some U. And then this is going to be U prime. Okay, so this is why this is going to be equal to U prime cross the product for I and I minus I prime xi. So this is the sketchy part here. Okay, so I'm just going to leave it at that. Okay, I'm going to be repeatedly using a fact. Fact I will use often. The fact I will use often is that, so we'll take A and B schemes, and what we'll be able to do is we'll be able to take A cross B, and we'll be able to take, sorry, you weren't supposed to know about that error yet, we'll take A cross B, and we'll take B, and we'll have this projection here, and then we can take some closed immersion here. And what I want to say is that if this is affine, then this base change here, cross B of Z, so if this is affine, then we conclude that this is affine. So we kind of base change by the closed immersion, and the idea is that well, this is maybe even a proof. Well, this inverse image of a closed set is closed, and this is a closed immersion. We're going to be taking the inverse image here, and this is A cross B of Z, and these cancel, so this is just going to be like A cross Z. And so what we'll be using is that if this is affine, then this is affine. Okay, and so the closed subscheme of an affine scheme is affine, and that's the idea, because we're taking the inverse image of a closed immersion. And that's all we're going to be using. Okay, so here's the lemma. Here's another lemma. So we're going to need the hypotheses as before. Xi is going to be a bunch of quasi-compact things. We're going to need that this guy here exists. And this is where we're going to see trouble right away. So this is the part where we're going to see trouble. The other thing that we're going to assume, three things, there exists a closed point. And so in general, I'm going to say that we're going to have a bunch of closed points. In products, when we assume products exist, we're going to assume the closed points exist. Okay? So I'm going to say that there exists an I prime subset of I, which is finite, such that the following is true. When we take the product over all of these guys, which are not in this set, this thing is affine. Okay, so the product existing implies that it's almost affine. Up to a finite number of factors, when you take the product, it must be affine. Okay, so this is what I want to say. So this is bad news number one. Bad news. Okay, the first bad news, I'm going to show you how to prove the first bad news. So here's the proof. What we're going to do is we're going to take x, the closed point. Okay, we're going to let U contain X. This is going to be some affine open containing the X. Okay, and by the lemma, first lemma, well, we're going to have U looks like a product. And so this is and this is a affine. So this is an affine open set. This is affine, and this already looks like trouble. Looks like trouble already. This looks bad. Okay, so let me continue with how to prove this. So I'm going to apply that thing that we already said. So let's take x prime pi of I prime of x, and this is going to be in U prime, and this is going to be closed. Okay, this is a little shady. I didn't explain this, but let's suppose this. So suppose this. Okay, then what are we going to have? Well, I'm gonna look at like an FPQC covering, which is affine. I'm gonna do that thing that I was talking about that I'm gonna use all the time. So we have this product here, and we have a certain FPQC covering, which is given by these guys, where I base change to K prime, where K prime is equal to the residue field of this X prime, and X prime is this point here. This thing just looks like here, well, let me write down here. This thing is this product of these xi's for I away from I prime with this X prime here. This is just kind of the definition of the base change, and so it's enough to show that this product here is affine. So this is what we want to show. We want to show that that thing's affine, because we're going to use FPQ descent here. Okay, well, let's look at the thing. So we apply our fact, our commonly used trick. And you can look back on the video and see how we did it again. So we have I set minus I prime of xi cross u prime. And here, this goes to u prime, and we have this closed immersion of this point. So this point is a closed point. In particular, it's a closed subset. So this thing here is affine, we know. And then we have this thing here of I set minus I prime. This is xi cross x prime here. And we have this projection. And we got this by base changing, so we can conclude, that so this is I, and here this thing is affine. Okay, and so this was enough to show by this FPQC descent for this here. This was enough to prove that this was affine. Okay, so the next thing is I'm going to have to show a product that I'm going to have to, so affine things are automatically separated. And I'm going to have to use some things about separation. So let me give you a definition. So this is from the opposite category of schemes to sets. We just take a functor. And so I'm going to define separated for a functor. We say that X is separated if and only if for every Y and every two maps, every setup like this where we have two F's and Y's to here, then the equalizer of the two maps, so this is the equalizer here, this goes into Y, as this is a closed subscheme. Okay, so this is what it means for a functor to be represented, a functor. So this doesn't even need to be a scheme here. This makes sense. This makes sense as a subfunctor, but we need it to be a closed subscheme. So this is what it means for a functor to be separated. Okay, so let me give a lemma. Let me just skip this. Let me skip to the next page, and let me state the lemma that I want to prove now. So let's say that one, if this infinite product of xi's. So now instead of restricting to the whole that finite thing, I'm gonna show that each one of these is separated. So if this whole product is separated, if it exists and it's separated, then this implies that for every I, this guy is separated. Okay, so we're going to assume this. We're also assuming, so we assume this, and then we're also going to assume that existence of closed points. Okay, so I didn't prove that, but this is true. Proof. But I'm just going to keep it in the hypothesis. Okay, so suppose that x, I'm going to show that each one of these guys is separated. Xi is a closed point. Okay, so okay, so then we're going to have this k of x over k. This is going to be a finite extension. Okay, so what we need to do is that if we're given some kind of equalizer diagram here, we want to show that this equalizer that we have a closed immersion here. So this is what we need to prove. Okay, to show that for each xi, we need to show that this is separated. Okay, so given this diagram here, what I'm going to do is I'm going to construct a new diagram by tensoring up to k. So this is a thing of k-schemes. So, and what we'll do is we'll just change. This is the base changed version, and this goes from xi, and now we have this product. So okay, so here ki goes into the product. So we have this in here, but really we can view this as a map from spec of this thing into here. That's what this is doing, and it's going into here, j not equal to I. Sorry, this is for j not equal to I. Xj. Okay. Okay, xj like this, and so this is just equal to the product of these xj's here. Okay, and then we suppose that so this is as before. So this thing is affine and separated. So separated. Okay, so by separation, this implies that this equalizer here, that we have this closed immersion into here, okay, but we also have that here that the equalizer is equal to this equalizer, base changed, okay, and so this guy here. Well, this is an element of a closed immersion into y with kappa base changed, and so by effective descent, for closed immersions, so the Grothe and Dixer theorem, this implies that E of Fg is closed. Okay, this is a little shady as well, but I'm just going to move forward. Okay, so this concludes this proof. Let me get some more paper here. Okay, so let me give you the proof of the main theorem now. And so what have we done? Let's just recap real quick. So we showed that when we have this thing that's affine, right? In particular, we showed that the infinite product is separated, then this whole thing is separated. But we're going to know that this whole thing is affine, so in particular, it's going to be separated. Okay, so we're going to have each piece is going to be separated. We also had this type of so we had the bad shape here. Okay, and then we had this bad shape. And I think maybe that's oh, and then we had the big product. A big chunk of it was affine. So we had, sorry, we had the bad shape, and then we had that this big chunk was affine. Yeah, that's what this is. So that this big chunk was affine. Sorry. Ooh, what's the marker? Okay. Okay, whatever. We had those two things, and so I'm going to kind of clump those together. So in the proof of the thing, we wanted to show that all but finitely many are affine. So without loss of generality, let's just assume that this whole product is affine. Okay, because we already showed that the big chunk was affine, but we're assuming that the big chunk is affine, and we need to show that each xi is affine. Okay, so here's what we're going to do. We're going to apply the trick that so the idea is to apply the trick that we were always going to apply every time. So let me see if we, so here's the thing. Remember this thing that I'm going to use often. Okay, so I'm going to do the same thing again. Okay, so we're going to assume that, take z here, let's say in xj, let's say this is a closed point. And now I'm going to do the diagram. And then we have this projection onto the part where, let's say, j not equal to I here. Like this. And let's say all the j's. Okay. And then we have, in this, we have this closed point. This is really spec of the residue field. And we had this closed immersion, so this IZ, I don't know, we can call it IZ. And okay, so this is a closed immersion. And again, we have this thing where we have this product here, I, and then we have the product, the fiber product over here, this thing. And so this thing is really just xi with, so these all cancel, right? And this thing becomes xi base change to this residue field of z. Okay, and again, remember that this thing was affine. So this implies that this is affine. Because again, this is a closed subscheme of this. And closed subschemes of affine schemes are affine. So this is affine. Okay, so we conclude that xi k is this thing is affine. Okay, but notice this thing here, xi base change to this residue field. This is an FPQC cover. Okay, and this is affine. Okay, so by effective FPQC descent for affine morphisms, this implies that xi is affine. Okay, so, and we're done. So we've shown that all I is affine. Again, so what did we show? We showed, what did we prove? We proved that, so given that infinite products have points, infinite products having points, having points. The following. It says that this infinite product of xi existing, so where these xi are quasi-compact here, if this thing exists, then this implies that for all but finitely many I, xi is affine for almost all I. All but finitely many. That's the point. Okay, so thanks for watching. I'm gonna use this. Oh, so actually, let me just say what the example. So this could be, for example, like quasi-projective. Anything quasi-projective. Okay, so like open subschemes of projective schemes. So for example, okay, so I forgot to say that, but yeah, so this is what we're going to use. So we're going to use this kind of thing to say that products don't exist. So this is going to help us show that certain jet spaces don't exist. The limits in particular. So like the limits as schemes. So by exist we mean, of course, this exists as a scheme over K. And then this thing, it means that this is affine for almost all I. Okay, thanks for watching. If you have any questions, let me know. Bye.